Welcome to the final stretch of talks for today. This is Git at GitHub Scale. My name is Taylor Blau. I'm a staff engineer at GitHub, where I get the privilege and honor of working on Git every day. My work at GitHub is kind of broadly speaking divvied up into two categories. I get to spend about half my time working on the open source Git project, spend time there triaging the mailing list, responding to bugs, submitting patches, things like that. And I spend about the other half of my time or so working on this thing that I call Git at GitHub. So broadly speaking, my goal there is to help teams within GitHub find and address problems scaling to bigger and bigger repositories and write code in order to achieve that direction. So today I want to talk about sort of three aspects of my work. First, I want to talk about what it's like to use and deploy Git at GitHub. So we'll talk about our fork model, where and why we use Git, and why we made those decisions. I'll also talk about a handful of features from the Upstream Git project that we've used at GitHub and the impact that we've been able to have. And finally, I'll talk about a handful of features that I and some others have written at GitHub that we've then shared with the open source community and the impact that it's had in both places. Let's start with Git at GitHub. First, a couple of numbers. GitHub has 200 million public and private repositories on github.com. And among those, we serve about 2.5 billion annual contributions per year. So that's every time somebody writes a commit or pushes the repo or opens a new issue, that all contributes to this number. So powering all of this is a lightly modified fork of the open source Git project we know and love, and we've called that fork at GitHub GitHub Git. It powers many of the internal APIs and processes that drive the website. Anytime you push or fetch or clone from GitHub, you're interacting with Git. It also powers our periodic maintenance jobs that we'll talk about a lot in this talk, as well as all the RPCs that drive the contents of the website. There's a handful of RPCs that aren't implemented using Git. We use libgit 2 for those. And I think by and large, I'll mostly skip over them in this talk. So what's in GitHub Git? The most boring answer is that it has a handful of uninteresting patches that are sort of specific to GitHub's infrastructure, things like logging or metrics, talking to other internal services, and things like that. But more excitingly for me, it's the home of all the new feature development we do in Git at GitHub. So here we implemented multi-pack bitmaps. It was a staging ground for a lot of the commit graph changes we sent upstream a few years ago. And it also is the permanent home for our tree-level git blame implementation, which we'll talk about in this talk. We deploy it continuously to github.com, often a few times a week, and we back merge with Upstream Git, usually one or two major versions behind the latest release. Our work basically looks something like this. You can see new work is happening at the bottom, those little black dots in between merges with Upstream Git. And we try to stay between one or two major versions behind the latest from the open source project. So a natural question is, why would we power this sort of ludicrously scaled product based on the open source project? We could have picked any technology, including rolling our own, to drive a lot of these operations. But we chose Git for a few things. First, we think Git is fast, and it's getting faster every day, thanks to the contributions from many of the folks that are in this room. We also know that it's battle-tested. It's running billions and billions and billions of times a day across the sort of collective of all developers' laptops in the world, and so we can count on the reliability of this product to work for GitHub too. We also know that it's secure. GitHub is the beneficiary of a huge open source community of people that are finding and fixing security vulnerabilities in Git all the time. But most importantly, I think using Git is a mutually beneficial choice, both for GitHub and the open source community, because each gets to drive improvements in the other, and that symbiotic cycle is pretty cool to me. Let's talk about a few of the features that GitHub uses from the open source project to drive contents on the website. We're going to touch on three. We'll talk about the commit graph and change path bloom filters, partial clones, and what you just heard from Elijah, a little bit on merge-ort. Let's start with commit graphs. Commit graphs are an upstream feature that was developed by Derek Stoley, my colleague, then at Microsoft, now at GitHub. And what they are, if you're unfamiliar, is an on-disk serialization of the data inside your repository's commits. So it stores a table of the root tree ID, the commit date, any parents and octopus edges corresponding to all of your commits. It looks something like this on disk. And what's really important about having something like this in place is that it allows us to sort of skip the classic parsing and deflating an object in order to read different parts of a commit, because we know we can just drive all of this stuff by table lookup. So it makes history traversals really fast by eliminating a lot of the costly steps. So we maintain these on the server. Every new push that you send to GitHub generates a new layer in the commit graph. And occasionally, we'll take many of these layers and squash them down into one slightly larger layer in order to keep the commit graph chain pretty small. We also use pretty importantly, these change path bloom filters, which were developed by Garima Singh while at Microsoft. And these store what is called a probabilistic set of the changed paths in each commit relative to their first parent. And so for any commit, we can ask, did this commit change path X? And we'll either get back the answer, it definitely didn't, or we'll get back an answer that says probably, and we can determine with high probability that that path was likely changed by that commit. And so we've been able to use all of this to accelerate a number of history traversal operations on GitHub.com that are scoped to specific paths by being able to ignore parts of history that we know don't change the path of interest. So I'm going to show you a few graphs of what it looked like to deploy that. Starting with git log, this powers all the history views on the website. You can see there where we deployed change path bloom filters and commit graphs, we were able to drive the P999, or the 99.9th percentile, down from about 1 3/4 of a second to just around 1 second. Here we're looking at the git blame operation. That's that line level history operation. There we were able to drive about a 40% reduction in the 99.9th percentile by using bloom filters. And you can't quite see it, but there in the top right, we were able to drive down significantly that sort of flat horizontal line, which represent timed out operations, into a state where they would no longer time out quite as frequently at the top end for us. We also had a similar improvement in the tree level blame implementation that we use at GitHub. Here we were able to drive down the 99.8th percentile performance from about 3.5 seconds to just 2 seconds. And so we were really excited about this and being able to drop off some of the timeouts there at the top right. Let's talk a little bit more about blame tree, though. So blame tree is a custom command, like I've said, that provides the tree level blame information on github.com. So if you've ever noticed that second column in your repository tree views, it just shows the commit message of each commit to most recently touch every directory entry. And so last year, Derek Stoley and myself at GitHub thought that we could make this algorithm a little bit faster. So to tell you how we did that, we basically looked at the existing algorithm, which is sort of the naive approach, and it basically recursively does a tree diff at each level in history, assigning the current commit to each entry in the tree based on whether or not it was changed at that path and hasn't yet been blamed. And we just repeat that until either we reach the beginning of history or we've blamed everything in the directory. The new algorithm works a little bit differently. The general idea is to only compute tree-level blames where we need to. So we keep track of sort of the remaining interesting paths, or the unblamed paths, and we can skip over parts of history where we know that we've already assigned some commit to an entry. And then we pass any unblamed paths to the parents and continue until we either blame everything or reach the beginning of history. So we were able to deploy this again, and blame tree performance improved even further, moving the 99.8th percentile down to just 2 seconds, and we saw a significant drop-off in timeouts in that sort of 99.9th and top-level 99.99th percentile there at the top right. So we were really excited to see this operation succeed more quickly and more often for users on github.com. Next thing I want to talk about is partial clones. Partial clones are an upstream feature that was developed by Jeff Hostetler at GitHub and Jonathan Tan at Google. And they allow you to clone just specific parts of your repository. You can dictate this by specifying a filter option at clone time, which allows you to say, I just want blobs, or I just want trees of depth 0, and so on. Here's a few attempts of me cloning the Linux kernel from github.com. It's sort of a classically large repository to talk about. And you can see my best attempt over a pretty fast network was just shy of 5 minutes. That's the time it takes to get all the objects from GitHub necessary to build and compile the kernel. The partial clone, which just downloads the blobs reachable from the very root of history, takes just shy of 2 minutes. So we were really excited about being able to deploy this change on github.com to allow our customers to work more quickly in even bigger repositories just on their laptop. Finally, I want to talk briefly about GitHub's deployment of merge-ort. A lot of these details were covered in the talk just before, mine and Elijah's. But I want to talk about how this work sort of progressed on GitHub. So we compute merges all the time in the background on github.com. They power the existence of that merge pull request button that hopefully you're familiar with from the pull request view. The way these work basically is every time a pull request advances its state, we proactively try to compute the merge of its head and base in the background to see whether or not we will actually be able to merge that pull request when all of your builds have passed, for example. And then when you actually click that button, all we do is a reference update in the background in order to point at the merge commits that we've generated ahead of time. We used to power this at GitHub actually using the recursive merge engine, which was the predecessor to ORT. But the problem was this required a working copy in order to represent the conflicted state of a repository. Since GitHub stores bare repos, we actually had to temporarily spawn a hydrated or full working copy of any repository we wanted to compute a merge on, and then perform the merge there, copy the objects over, and spin down the copy. And you can imagine this is pretty slow, especially for large repositories. And so a number of years ago, my colleagues implemented the same strategy in libgit 2, which eliminated the need to have a working copy of the repository present. Most recently, Elijah and Johannes, both Johannes at GitHub and Elijah at Palantir, collaborated on bringing all the power and speed from ORT into Git Merge tree, which is a command that we've now used on the server side to power all merges on github.com. This work was done by my colleague Johannes at GitHub and Greg Hurrell. This was the result of deploying merge-ort to github.com. There were too many graphs to pick from, and this was just the most beautiful thing that I could have imagined. We were able to drive down the P99 times dramatically from sort of 6 or 7 seconds to well under a half a millisecond. So we're able to much more efficiently generate merges on the back end. Finally, I want to talk about a few of the features that I and my colleagues have developed at GitHub that we've sent to the open source project to achieve bigger and bigger scales at GitHub. So we're going to cover 4. I'm going to talk first about multi-pack reachability bitmaps. Then we're going to take a tour through 2 sort of sub-projects that were developed along the way. We'll talk about on-disk reverse indexes and geometric repacking. And lastly, we'll talk about a recent development that we've used to eliminate unreachable objects on github.com that we call Cruft packs. Let's start with multi-pack bitmaps. So a brief refresher. Every time a repository gets pushed to on github.com, we add a new pack to that repository representing the objects that were sent to us by the client. As more and more packs get added to the repository, the performance can degrade over time. And in order to keep repositories running smoothly, we do a periodic maintenance routine that effectively compacts the set of packs in a repository to make sure that performance runs smoothly. This is basically amounting to something like running the following, which takes everything and moves it into a single pack. And so you may be asking yourself, why would you actually want to take some of these ludicrously sized repositories and generate just a single pack of all of their objects? It seems kind of slow and wasteful. There's a naive answer, which is that any operation that needs to do object lookups has to consult all of the packs in your repository in the worst case in order to find the location of each object. So if you have just one pack, that operation becomes really, really quick. But the key point for us, much more important than the sort of speed of object lookups, was having reachability bitmaps. So what are reachability bitmaps? A bitmap allows us to very quickly answer the question, what objects are reachable from some commit? Every commit gets associated with a long bit string. Each bit in that bit string represents an object. And when a bit is 1, it means that that commit can reach that object. And when it's 0, it means it can't. This eliminates the need for object traversals. If you want to know the set of reachable objects from the tip of your main branch, you can just read them off of the bitmap instead of having to actually crawl throughout history. And so this is a crucial optimization for us at GitHub because those history traversals can often be unbounded. We're able to combine these bitmaps in sort of some cute and intuitive ways, like if you want to know the union of reachable objects across multiple bases, you can just take the bitwise OR of all of their bitmaps. Similarly, if you want to compute the set difference, say the objects that are reachable from some set of tips but not reachable from some other set of tips, like when serving a fetch, you can just combine these with an and not operation. So these bitmaps are great, but the problem is they can only encode information about objects that are contained in a single pack. And so that's the reason that we needed to pack all of a repository's objects down into just one humongous pack file. But for us, we noticed starting a few years ago that this operation became prohibitively expensive as repositories continued to grow larger and larger, that we often couldn't re-deltify and compress all of the contents of a repository into a single pack within our maintenance timeout windows. So to address this limitation, we turned to an upstream feature developed by Derek Stoley called the multi-pack index. The MIDX acts like a single index over multiple pack files, and I've drawn it a little bit here. So here's a cartoon that shows a few packs on the bottom of the screen, identified with some colorful little objects in between them. And the MIDX, which spans all of the packs, takes the unique set of objects described and contained in the packs of your repository, and it refers to the location both what pack contains each object and where in the pack you can look for the object. So we had this idea that we could start with the MIDX and define what we call a pseudo-pack order over it, that we would then use to generate a bitmap based on the contents of a MIDX. We thought if we could do this, that we'd be able to repack a repository into sort of any arbitrary structure of packs that we wanted, write a MIDX containing just the packs we want to keep in the repository, and then write a bitmap covering those packs. So we thought that would look something like this. There's my same diagram from earlier, extended with a bitmap on top, just with some randomly chosen 1s and 0s to indicate which objects are reachable. And we were really excited about this until I realized it wouldn't work, because there's no way for us to map the 5th bit, which points to the blue object, back to the blue object. Let me show you why this is the case. You would think that the way you would do it is by counting the number of objects in the packs prior to the one containing the blue object, and then knowing the pack relative position of the blue object in order to narrow down which bit pertains to it. But this doesn't quite work because you actually need to know not just the number of objects in each pack, but the number of unique objects across all the packs preceding the containing one. You can see there's actually 2 copies of the red object down below, but the MIDX only knows about 1 of them. And so you're going to be off by 1 in either direction when you try to go look for the blue object. So we knew we needed something better. To address that, we began sort of the first of 2 major side quests on this expedition to implement something called on-disk reverse indexes. So a brief primer. Packs, like we mentioned before, contain a sequence of objects in a semi-arbitrary order. Indexes map the objects in those packs to their map the objects in lexicographic order to the corresponding offsets in those packs. And reverse indexes do the opposite task. They take a pack of objects in their pack order and map them to the lexical order. So reverse indexes are something that's been in Git for as long as I can remember. These exist already and are used to power things like computing the on-disk size of some object. If you want to know the on-disk size of a given object, we'll look in the reverse index to find, we'll look in the index to find the position of that object, and then use the reverse index to find the position of the immediately adjacent object and compute their difference in order to determine the size. The way we do this is by generating it in memory on the fly, by radix sorting an array of an object ID and offset pair. This works. It uses the most sort of efficient sort that you can imagine in this regime. But it still takes time proportional to the number of packed objects, and more importantly, it's super memory intensive, because we have to store about 32 bytes worth of information for each one of these records. So not only do you pay the cost in sorting time and sort of persistent memory allocations, but it can often take your library measurable amounts of time to just allocate that much memory and hand it to you. So GitHub a number of years ago sort of improved the situation by implementing a sort of precursor to the on-disk reverse index as an optional extension within the bitmap format. This is a custom format that we developed at the end of the bitmap file. And it's a table of 4-byte unsigned integer values that each correspond to a packed object in the pack corresponding to the bitmap. And this table was stored in pack order, and each value is the lexicographic index for each object. And so when we were trying to address our problem of mapping that 5th bit to the blue object, we thought we could actually use this bit cache extension as a good starting point. So we decided that we could upstream it and then use it for multi-pack bitmaps, but that it required a bitmap to be useful because it was implemented as an extension in the bitmaps. And so we wanted to do something a little bit more general, and for that, we implemented the rev file. This is a new on-disk format that sits aside your packs, just like pack indexes. It can be used outside of the bitmap file, and it corresponds to both the packs and MIDXs. For packs, you can use it with or without bitmaps. And for MIDXs, it's really only useful if you have a bitmap today. This is a little bit of what it looks like. Here you can see I've drawn a pack with 3 objects, a red, yellow, and green one, which appear in that order in the pack. But in lexical order, you can see the yellow object precedes the red one, which precedes the green one. So if you're looking at the yellow object in the pack and you want to know what order does it appear in lexically, you can just follow the arrow to the reverse index and read off that value 1. And then if you look at the array subscript 1 in the index file, there's the yellow object. So we were pretty excited to deploy this at GitHub because we thought we could save some time by not having to sort through this big in-memory reverse index. And we were really pleased with the result. So this is the P50 fetch time for fetches on the homebrew core repository. This is a sort of classically or well-known, highly trafficked repo at GitHub. And so we were really happy to drop the runtimes in P50 from about 2.5 seconds to just under 500 milliseconds. And we actually saw this continue over all repositories at github.com. Here's just the sort of P50 through P99 runtimes in one single site, showing fetches across all repos in that site. And you can see we achieved about a 40% speed up there. Most importantly, though, we were able to use this to untangle our problem from a few slides back. So you can see, if you want to discover that the 5th bit pertains to the blue object, you just follow the arrow down, read the 5th array element in the reverse index file, and you can see that it corresponds to the 11th index in the multipack index file. And I'll spare you the counting, but if you go 11 spaces from the left there, you'll end up at the blue object. So now that we have this in place, we thought we could define a pseudo-pack order of all the objects in the MIDX, which appear themselves in pack order, And then we arrange the packs by sort of grouping them according to how new they are. And we eliminate ties in favor of sort of this preferred pack. We store this order in either an on-disk reverse index file or as an extension within the multi-pack index more recently. And we use that to be able to translate bit positions from the bitmap to the corresponding entries in the MIDX file. So now that we had sort of unlocked this arbitrary pack structure capability, we needed to figure out how we were going to repack repositories at GitHub. So to do that, we implemented something called geometric repacking. When we were searching for sort of what strategy we wanted to use, we knew that we wanted to achieve two properties. One, that on average, relatively few packs would remain after doing repository maintenance. That's key for that sort of object lookup speed thing that we were talking about a few minutes ago. And we also wanted it to be the case that on average, the work required to get to that new pack structure would correspond roughly to the number of new objects that have entered the repository since the last maintenance run. And the simplest approach that we could think of that would capture those sort of two properties was to make the packs appear in a geometric progression of sorts. So the idea there is that each pack contains at least twice as many objects as the next largest pack. So let me show you a little bit about how we compute those. Here's a pack structure. There's about 7 packs here. And you can see the green ones I've colored. The first step is to identify how many large packs already obey this property. We're sort of doing this geometric repacking thing all the time, and so we expect the bigger packs, which are going to change on average less frequently, to mostly already be in this progression. So we count off and we say, OK, the top 5 packs are already in progression. And so I know everything to the left of that line is going to have to get repacked into one single new pack. But as soon as I do that, I'm going to throw off my progression, because the first pack will contain 2 objects, but the second pack will only contain 1. And so we violated that doubling property. So we then expand the line in order to figure out how many packs we need to sort of compact together at the low end of the spectrum in order to restore this property. So here you can see in this example, we need to combine the 4 smallest packs together in order to restore that geometric property that we talked about. And that's what we end up with as a result. So between on-disk reverse indexes, geometric repacking, ultimately multi-pack bitmaps, we're able to deploy all 3 of these together to achieve a pretty dramatic reduction in the time it takes to maintain repositories on GitHub. The blue line there is the sum of all time we've spent in maintenance on sort of an individual basis. And the gray line that's just above it is that same value from a week prior. In case you're having a hard time reading the y-axis, I'll tell you that we saved 5 and nearly 2/3 of a CPU day every single hour on github.com with these changes. And we're really excited about that. Finally, I want to talk about a sort of more recent development that we've made to clean up unreachable objects at GitHub. You may be wondering, what is an unreachable object? Well, they're all the red ones in this picture. So an object is reachable when you can start at some branch or tag, walk throughout history, and find yourself at that object. Walking, I here just mean to say you started a commit and you look at its parents, or a tree and look at its subtrees and blobs and so on. Any object that satisfies that property gets colored blue, and it means it's reachable here. Any object that doesn't is red, and it means it's unreachable. So we have kind of a lot of these at GitHub. They come from all sorts of places. Test merges, force pushes, branch deletions. Any of these can create a set of unreachable objects. And historically, we've let these grow without bounds. So we'll almost never clean up unreachable objects unless you ask us to. But sometimes we do have to clean up unreachable objects. So users will request a manual cleanup, say, to remove sensitive data they accidentally entered into a repository, or if they notice poor performance and they just want to clean up, do some spring cleaning, we'll help them out with that. So support engineers respond to these requests by running the .gc command in chat, which triggers a garbage collection. And it basically causes us to run something like the following, which has this unpack unreachable keyword at the end of it. What this does is it takes all the reachable objects and moves it into one pack. It takes any unreachable objects which haven't been written to within the last 5 minutes, and it just deletes them from the repository. And then anything that is unreachable but has been written within the last 5 minutes gets stored as a loose object. You can remember the very first talk of the day where we discussed what loose objects are here. So why have this cutoff? Why not just delete all the unreachable objects at once? And the problem is that there's a little bit of a race between object deletion and object advertisement. Let me explain what I mean there. So suppose you're a Git server, and you decide that you want to prune and just remove this object C, which we'll say here is a commit. If before you actually do that, C becomes made reachable by some ref update or just background operation, and then another client starts a push, they're going to hear about C via the reference advertisement, and then they may send you a pack that contains C in it, Or worse, it depends on C in some way. In that case, objects are going to then enter the repository which are dependent on C, either by referring to them or being stored as a delta amongst them. And if all of that happens before C actually gets removed, then you have objects referring to C in the repository without actually C itself. So that leaves the repository in a corrupt state. So what we do to accommodate this, or what Git did before our recent changes, is that it would store these sort of pretty recent unreachable objects individually as loose files. The stat level m time of each loose object file would track the object's age, and then rewriting the object, which just means anytime we sort of wanted to write it as a new object entering the object store, we just take that existing loose file and set its m time to the current timestamp. And this works fine. It, in practice, makes the race that we described a few slides ago less likely to happen. But it has some other problems. Namely, if you have a lot of unreachable objects in your repository, it can result in creating many loose object files, especially if those unreachable objects have been written to relatively recently. It has some other drawbacks, too. If you have pairs of unreachable objects which have very similar contents, because they're stored in separate loose objects, they're not allowed to deduplicate amongst themselves and share contents. But the most important problem that we faced is that having too many of these files can lead to significant performance problems, including inode exhaustion, which basically we were able to observe at GitHub. A single repository garbage collection would annihilate the machine hosting many thousands or tens of thousands of repositories in one fell swoop. So to address this, we introduced this concept that we now call the Cruft pack. This is an old idea that was originated by Jeff King on the mailing list. And the idea is relatively simple. You take a pack and its index, and you associate all the objects in the pack with an m time that's written as a table of integer numbers in an m times file. So you no longer have to store each unreachable object loose. You can just read the value in the m times file. And anytime we say that a pack has both an index and an m times, we can group that into a concept that we call Cruft packs. So the remaining part of my time, I want to talk about how we generate those Cruft packs. There's two cases. There's sort of an easy case and a little bit of a harder case. The easy case is when we know that we're not going to expire any objects out of the repository. All we have to do there is mark all the reachable objects, create a pack containing them, then take any remaining objects which didn't show up in that pack, and pack those separately along with their m times and delete all the existing packs. When we're doing object expiration, it's basically the same process as above, but we don't want to pack all the unreachable objects. We just want to pack the ones that we know are old enough, that we know are new enough to need to remain in the repository. Any old objects will get deleted, except before we actually create that pack, we want to traverse any unreachable objects that were new enough to stay around in the repository and rescue anything that we were able to reach along the way. And the idea here is that if a cluster of unreachable objects gets partially deleted, and then that cluster then becomes reachable via a later update, that repository would be in a corrupt state because it'd be missing some of its reference. But if we keep around all of the objects in unreachable clusters, as long as at least one of them is surviving, then we can eliminate, or at least significantly reduce the likelihood of that happening in the future. So let's go through a few animations here. So first, this is how we generate objects, generated Cruft packs without object expiration. We mark all of the reachable objects by starting at each branch tip and following the arrows throughout history, coloring them a slightly darker shade of blue. And then we take a look at all of the objects in existing packs and scan for their existence in the new reachable pack. We're going to color them green if we see them. In that case, we know they're reachable, and red if they aren't, in which case we'll mark them as unreachable and generate a new pack containing just those objects. When we want to generate a Cruft pack with object expiration, like I said earlier, we want to keep unreachable objects in clusters around in either a sort of all or nothing state. So if any part of a cluster that's unreachable is too recent to be actually deleted from the repository, we keep all of those clusters. And we perform that by doing a reachability traversal over the recent objects. Here you can see we take all the unreachable objects and start at just the ones that are new enough to stay in the repository, marking them as we see them. And those objects then get entered into the Cruft pack instead of being pruned. We use this at GitHub by geometrically repacking the repository sort of every 8 out of 9 operations. And the 9th maintenance job collects repositories into a reachable and a Cruft pack. In normal course of maintenance, we don't bother to ever prune these objects. So we do a repack Cruft with no expiration. But GitHub support can still respond to requests from our customers by running GC repo, which instead of unpacking unreachable objects, now has a Cruft expiration parameter. I want to talk about one more thing, which is that we still have the problem of being unable to, in a race-free manner, prune objects from the repository. So my colleagues had an idea that instead of eliminating this race entirely, we could actually use Cruft packs to make it far easier to recover from. So this is joint work with my colleagues Michael Haggerty and Torsten Walter from GitHub. And the idea was to move every unreachable object that we were going to delete from a repository into a separate Cruft pack that was stored outside of the repository. We can then, after we do that, do an integrity check on the main repository to ensure all of its objects are still present. If they aren't, we'll restore them from what we call the limbo repository, and then remove the limbo repository once we're done. So the limbo repository, crucially, is really just another Cruft pack, but it has two tweaks. One is that generating that Cruft pack will exclude any objects that it found in both the reachable and Cruft packs in the main repository. It also doesn't have any sort of pruning conditions, and so every object that it sees that meets the above condition ends up in the limbo repository. So this means that every object that would have been pruned during a normal GC ends up in the limbo repository in the destination specified by this sort of experimental expire to option. And I have some RFC level patches that explore this concept on the mailing list for anybody curious enough to try it out. So to recap, I'm going to leave you with 4 things. Git is a reliable, fast, and secure implementation that can be relied upon even at GitHub scale. GitHub gets to use features from the open source Git community, including partial clones, commit graphs, the multi-pack index, and merge-ort. And GitHub also contributes tools that it develops back to the ecosystem, like multi-pack bitmaps, Cruft packs, and more. Finally, what I want to say is that the same tools that power GitHub.com can and do run on your laptops all the time, and I think that's pretty cool. Thank you.